Hi everybody. In the previous video we introduced the first law of thermodynamics. In this video we're going to talk about some of the implications of it, including the importance of state functions, calorimetry, and enthalpy. We've seen in previous videos that the internal energy of an ideal gas, which we represent by the letter U, depends only on its temperature and the number of moles. In general, the internal energy of a system that is not an ideal gas can depend on other things like pressure also. But it's always the case that internal energy is what we call a state function. It's a function only of the current conditions of a system. It doesn't matter how the system got to its current conditions, it doesn't matter where it was yesterday, etc. And a lot of the properties that we care about are state functions. Things like temperature, pressure, and volume. These are all things that we can measure only seeing the current state of a system. But we've seen some examples of quantities that are not state functions, including heat and work, which we introduced in the previous video. We saw that the amount of work that's done when going from initial conditions to final conditions depends on the path that you take through a pressure-volume diagram. So you need to know how a system got from point A to point B in order to know how much work was done. And the same is true of heat. If internal energy is a state function, but work depends on path, then we know that heat must also depend on path in order for the first law of thermodynamics to always be true. You may be wondering why this distinction between state functions and what we can call path functions is important. It seems a little bit pedantic at first. To explain, I'll use the example of altitude, which is a state function. You can be at any point on Earth and know unambiguously what the altitude is, regardless of how you got to that point. That means that if you want to know the difference in altitude between point A and point B, you can take any path you want from point A to point B, and if you measure the changes in altitude, whether you're going up or down, you can find the difference in altitude between point A and point B, regardless of whether you take one of these two paths or any other path that you could imagine. You can take whatever path makes it easiest for you to measure differences in altitude. The reason why this matters to us is that using state functions can be really helpful when we're thinking about chemical reactions. We often care about the changes in energy in going from reactants to products in a chemical reaction, and changes in energy along a reaction pathway can be really hard to measure. Often some bonds are being partially broken, as others are being partially formed, and it's tough to keep track of changes in energy every step of the way. But for something like internal energy, which we know is a state function, we don't actually need to know the real reaction pathway. But we can think about whatever reaction pathway makes it easiest for us to think about changes in internal energy. For example, we can do something like take all of the reactant molecules, break all of the bonds so that the molecules are all separate atoms, and then bring all of those separate atoms together into the products. That's not actually what happens during a chemical reaction, but thinking about things that way can make it easier for us to evaluate changes in a state function like internal energy. Before moving on, I just want to introduce one piece of notation, and that's the distinction between exact and inexact differentials. When we're dealing with state functions like internal energy, we use what are called exact differentials, and these are essentially the differentials that you're used to from calculus class. If we want to integrate the change in internal energy from some initial state 1 to some final state 2, we take the integral of du, and that du is the notation for an exact differential. And when we evaluate that integral of du, we end up with delta U, the change in internal energy from the initial state to the final state. So exact differentials are what you're used to using in calculus. But when we deal with path functions like heat and work, we use what are called inexact differentials, and they have the notation delta Q or delta W. In this case, when we take the integral of, for example, delta Q from state 1 to state 2, the path matters. The result depends on what path we take from state 1 to state 2. So in the case of path functions and inexact differentials, it doesn't make sense to talk about changes in heat or changes in work, for example. You can't say that a system at its final state has more or less heat than it did at the initial state, because heat transfer depends on what path you took from state 1 to state 2. In this course, we won't really be evaluating path integrals using inexact differentials like this, but I wanted to introduce this distinction in the notation. So far, when we've looked at concrete examples of energy transfer, we've been looking at the energetics of changing physical variables like pressure and volume. But this is a chemistry course, and as chemists we usually care more about bonds breaking and forming, and the energetics of processes like that. And when we measure the energetics of chemical reactions, calorimetry is the most common tool. This picture shows a simple coffee cup calorimeter like you might have used in a Gen Chem lab. In this picture, the reaction that's taking place is a neutralization reaction between hydrochloric acid and sodium hydroxide. And the way that calorimetry works is that when this reaction happens, any heat that's released is then taken in by the water and calorimeter setup, raising the temperature of the water. And then by seeing how much the temperature changes and knowing the heat capacity of the calorimeter, you can figure out how much heat was transferred. Conversely, if the reaction takes in heat, then the temperature of the calorimeter goes down, and you can again measure that change to figure out how much heat was transferred. So, in calorimetry, what you're directly measuring is Q, the heat transfer of a reaction. And although it's useful for us to know how much heat is transferred, it's not exactly what we want. Ideally, we'd be able to measure the change in some state function, because we know that state functions don't depend on path. So if we know the change in a state function, we know something about the energetics of the reaction that's independent of what path that reaction took. So, let's start to think about how we can relate heat transfer to state functions. The first state function that comes to mind when we think about energetics is delta U, because we've already talked about changes in internal energy. The first law of thermodynamics tells us that delta U, the change in internal energy, equals Q plus W, heat transfer plus work. So in general, changes in internal energy are not the same as the amount of heat that's transferred. But under certain conditions, those two things can be equal. Specifically, if we're looking at constant volume conditions where there's no work done, the first law of thermodynamics becomes delta U equals Q. So at constant volume, if we know the amount of heat that's transferred, we know that that's the same as the change in internal energy of a reaction. We can write this as delta U equals Q with a subscript V, meaning delta U, the change in internal energy, equals heat transfer at constant volume. And it is in fact possible to do calorimetry at constant volume. This is a picture of what's called the bomb calorimeter, where a reaction takes place in a bomb cell that's a rigid container that has constant volume. And when that reaction takes place, the temperature of the water in the calorimeter changes, and by measuring that, we can measure the heat transfer of the reaction, which, as we said at constant volume, is equal to the change in internal energy of the reaction. So, in a bomb calorimeter, we can relate heat transfer to a state function, the change in internal energy. But there are a couple of drawbacks to bomb calorimetry. First of all, a bomb calorimeter, which has constant volume, is more expensive and more complicated to set up than a coffee cup calorimeter, which has constant pressure. And second of all, we as chemists are more often concerned about constant pressure conditions than we are about constant volume conditions. Most of the chemistry that we do is on the benchtop at constant pressure. So it's more important for us to be able to relate heat transfer to a state function at constant pressure than it is at constant volume. And although we just saw that changes in internal energy easily relate to heat transfer at constant volume conditions, that's not the case at constant pressure conditions. Delta U is not the same as Q at constant pressure. So the next question we're going to ask is there some more convenient state function that relates to heat transfer at constant pressure? Again, we'll start with the first law of thermodynamics, delta U equals Q plus W, and use our definition of pressure volume work to replace the W with minus integral of pressure times dV. At constant pressure conditions, which is what we're looking at here, we can replace that Q with a Q subscript P, heat at constant pressure. And because pressure is constant, we can take the P out of the integral and replace the integral of P dV with P delta V. And then we can isolate heat at constant pressure, which is what a constant pressure calorimeter is going to measure, and say that that's equal to delta U plus P delta V. Everything on the right side of this equation, internal energy, pressure, and volume, these are all state functions. So we can already see that we've related heat at constant pressure to state functions. but we're going to do something a little bit more compact. We're going to define a new quantity, enthalpy, which we symbolize with the letter H, and say that it's equal to U plus PV. Because enthalpy is a combination of other state functions, it itself is also a state function. Given this definition, a change in enthalpy delta H is equal to delta U plus delta, the quantity of pressure times volume. And at constant pressure, which is the condition that we're concerned about, we can bring that pressure out front and say that delta H is equal to delta U plus P delta V. Notice that the right side of this equation is the same as the right side of the equation up top, so we can say that all of this is equal to Q at constant pressure. Therefore, with this definition of enthalpy, we now have a state function that relates directly to heat transfer at constant pressure. Chemists very often talk about changes in enthalpy because they're measurable with a constant pressure calorimeter like a simple coffee cup calorimeter, and they're relevant to energy transfer in reactions that happen on the bench top at constant pressure conditions. Because enthalpy is a state function and changes in enthalpy don't depend on path, changes in enthalpy are transferable to different conditions, and as you probably know, they're often tabulated for reference in the backs of textbooks. In our coverage of statistical mechanics, we talked a lot about heat capacity, and when we did that, we were always talking about the constant volume heat capacity. At this point, we're in a position to understand that heat capacity depends on conditions, and the constant volume heat capacity is actually different from the constant pressure heat capacity. The reason for that is at constant volume, all the heat that goes into a substance goes toward increasing its internal energy. It goes toward raising the temperature. But under constant pressure conditions, when heat is transferred to a system, some of the heat goes toward causing the system to expand, especially if that system is a gas. And only the remaining amount of heat goes toward raising the temperature of the system. So before we do any math, I'll ask the question, which of those two heat capacities, constant volume heat capacity or constant pressure heat capacity, do you think is larger? I'll give you a few seconds to think about it. Well, remember that heat capacity is basically the amount of heat that's needed to raise the temperature of a system by a certain amount. So at constant pressure, more heat is needed because some of the heat goes toward causing the system to expand. So that means that in general, constant pressure heat capacity is larger than constant volume heat capacity. This distinction is mostly important for gases because gases expand a lot when they're heated up. Because the volume of a liquid or a solid doesn't change very much when it's heated up, the constant volume and constant pressure heat capacities of liquids and solids are nearly the same as each other. I'd like to take the example of a monatomic ideal gas and think about how different these different kinds of heat capacity actually are. In general, the definition of heat capacity is heat divided by change in temperature. As we've seen, heat under constant volume conditions is equivalent to internal energy. So the constant volume heat capacity of a system is the partial derivative of its internal energy with respect to temperature at constant volume conditions. That's a definition that we've already seen. Because, as we saw a couple of slides ago, enthalpy is equivalent to heat at constant pressure. The constant pressure heat capacity of a system is the partial derivative of enthalpy with respect to temperature at constant pressure conditions. So let's think about how these two expressions relate to each other. Using the definition of enthalpy, U plus PV, we can say that the constant pressure heat capacity is the partial derivative of the first term, partial U partial T at constant pressure, plus the partial derivative of the second term, partial PV, which can be replaced by nRT using the ideal gas law, with respect to temperature. The first term of this expression almost looks the same as the constant volume heat capacity. One of them is at constant volume and one of them is at constant pressure. But when we remember the fact that for an ideal gas, internal energy only depends on temperature and it doesn't depend on pressure or volume, we can see that this first term is actually equivalent to the constant volume heat capacity. So the first term is just CV, and in the second term we can bring nR out front because those are constants, and we're left with just partial derivative of T with respect to T, which is just 1. So we found that for any ideal gas, we haven't yet specified a monatomic ideal gas, Cp, the constant pressure heat capacity, is equal to Cv, the constant volume heat capacity, plus Nr. So because an ideal gas expands a lot when it's heated up, these two types of heat capacity are actually pretty different from each other for an ideal gas. And for a monatomic ideal gas specifically, we've already seen the value of Cv in our past coverage of statistical mechanics. It's equal to 3/2 Nr. So that means that if Cv equals 3/2 Nr, and we just found that Cp is Nr more than that, then Cp, the constant pressure heat capacity, must be equal to 5/2 Nr. And again, it's true for all ideal gases that Cp is always Nr more than Cv. For the last few minutes of this video, I'd just like to talk about a couple of ways that we can take advantage of the fact that enthalpy is a state function to learn about the energetics of chemical reactions. The change in enthalpy of a chemical reaction, delta H with a subscript R, I'm using the same notation as Macquarrie, is just the enthalpy at the end of the reaction minus the enthalpy at the beginning, enthalpy of products minus enthalpy of reactants. Typically, we use the word exothermic to describe a reaction in which the enthalpy of the products is lower than the enthalpy of the reactants, and we use the word endothermic to describe a reaction in which the enthalpy of the products is higher than the enthalpy of the reactants. And what's important to note is that because enthalpy is a state function, if we're interested in finding delta H for a chemical reaction, we can imagine that reaction proceeding by whatever series of steps we want, whether or not it's actually the series of steps that the reaction goes by. Two implications of this, which you've probably seen back in your general chemistry courses, are Hess's law and the idea of standard enthalpies of formation, and I'd like to spend a couple of minutes just reviewing those topics. Let's illustrate Hess's law by example, using a problem from Macquarrie. In this problem, you're shown two chemical reactions and told delta H for each of those reactions under standard conditions. The little circle means standard conditions. And you're asked to find delta H under standard conditions for another reaction. The idea of Hess's law is that if we can express the overall reaction as a sum or difference of the steps that we know the delta H is for, then we can find delta H of the overall reaction. This is true regardless of whether or not the overall reaction actually proceeds by these two steps. In this case, and you can check my math on this, it turns out that the overall reaction at the bottom can be expressed as 4 times the first reaction minus 2 times the second reaction. In other words, if we took the first reaction on the slide, hydrogen and fluorine combining to make HF, and we multiplied that reaction by 4, and then from that we subtracted 2 times the second reaction, hydrogen and oxygen combining to make water, we end up with the overall reaction for which we're trying to find delta H. So that means that delta H for the reaction of interest is just 4 times delta H of the first step minus 2 times delta H of the second step. And again, you can check my math, but this comes out to minus 521.6 kilojoules per mole. When I say kilojoules per mole, I mean kilojoules per mole of the reaction as written. In other words, 2 moles of fluorine combining with 2 moles of water to make 4 moles of HF plus 1 mole of oxygen. That reaction has a delta H of minus 521.6 kilojoules. And again, Hess's law works regardless of whether these are actually the two steps by which the overall reaction proceeds. Another thing that we can do to find delta H of a reaction is to imagine that the reactants break up into their constituent elements, and then those elements come back together to form the products. This is not what usually happens in a chemical reaction, but again, because enthalpy is a state function, we can imagine the reaction proceeding in whatever series of steps we want. The reason why it's useful for us to imagine the reactants breaking up into their elements and then coming back together is that standard enthalpies of formation, in other words, delta H for elements coming together to form a particular molecule at 25 degrees Celsius and 1 bar, are often tabulated in the backs of textbooks. That means we can basically look up delta H for reactants breaking up into their elements, and then look up delta H for those elements coming back together to form the products, and find the energetics of an overall reaction by doing that. If we have an overall reaction of this form, A moles of A plus B moles of B forming Y moles of Y and Z moles of Z, delta H for that reaction is going to be equal to the sums of the enthalpies of formation of the products minus the enthalpies of formation of the reactants. This is something that you've probably seen before in general chemistry. One thing to note about this is that in order to tabulate enthalpies of formation, we have to set a somewhat arbitrary definition of what has an enthalpy of formation of 0. And we do that by defining what are called standard states of the elements. So things like graphite or oxygen gas, etc., those are defined to have an enthalpy of formation of 0. Finally, just a few takeaway messages from this video. We've seen that using state functions like internal energy and enthalpy are particularly useful to us because they don't depend on path. So those values are transferable and they can be tabulated in the backs of textbooks. And they allow us to think about reaction energetics without actually knowing what the mechanism of the reaction is, as we just saw with Hess's law and the idea of enthalpies of formation. And while the experimental technique of calorimetry is actually measuring heat transfer, which is not a state function, we've seen that under certain conditions, like constant volume and constant pressure, we are able to relate heat transfer to changes in state functions like internal energy and enthalpy. That's all for now. In the next video, we'll be moving on to entropy and the second law of thermodynamics.